How's life? It's pretty good. Um, so in terms of refreshing, I tried this with my 31B review session the other day. The chat broke and I refreshed and it ended the stream. So I don't know if there's something else I can do. Favorite type of eggs. If that means how to cook them, I make a lot of frittatas. That's my favorite kind of way to eat egg. Favorite sports team, the Northwestern Wildcats by the UCLA Bruins. What's my favorite TV show? Not a very interesting answer, but The Office is up there. Breaking Bad is up there. The Great British Baking Show is up there. Do I watch soccer? Not really. I was a fair weather fan when the USA was doing well in the World Cup a few years back. I watch a lot of basketball, yeah. What type of music do I listen to? You can check out my website. You can creep on that. How much can I bench? Probably 215 to 225. Favorite muscle group to hit?
I feel like you get
every single time. Probably triceps. Favorite basketball team? The Northwestern Wildcats. Yeah, I need to pay more attention to women's sports. The Northwestern women are killing it, and well, basketball's over. They were killing it. The women, Northwestern women, won the Big Ten championship. So, yeah, I watch the NBA too. I'm more of a college sports fan, but I follow the NBA. Okay, we'll get back to the math. Oh, Steve. Yeah, the tattoo is my heart rate. So this is one day, and then this is another day. And this was a very bad day and a very good day, to keep it short. Favorite band, Hop Along is up there per my hat. Ariana Grande's up there. Women that play basketball inspire me too. I suck at basketball, but I love it. All right, let's go back to math. I don't even remember what we were doing. Oh yeah, we started the second solution, which is to minimize some kind of distance function. But the thing to be careful about is that this function that I wrote down here is so, but we only care about points restricted to x plus 2y minus z equals 1. That was scary. Okay. Now, we are not doing Lagrange multipliers, but if you know about that, you could turn this into a Lagrange multiplier problem. Could do Lagrange multipliers. But we're not going to do that. We don't have to. We can turn this into a regular two-variable optimization problem by, for example, solving for z here and plugging that up in there. That would turn this into a two-variable function. So the points we care about satisfy the restriction z equals x plus 2y minus 1. So let me define something. So I would let little f be a function of two variables, and that function is going to be x minus 1 squared plus y minus 2 squared. Plus quantity z minus 3 is this minus 3. So that would be x plus 2y minus 4, quantity squared. And this expression right here, now that I've imposed this restriction, that describes the distance from any point on the plane that we care about to this point 1, 2, 3. So this is the distance from any point on plane to 1, 2, 3. Okay, that's the thing that we want to minimize. How's that so far? Yeah, I'm a big pop music fan. Okay. So far, so good. Now we have a minimization problem. How do we minimize a function? Look for critical points, blah, 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 go for there. Okay, so critical points are going to occur when the gradient of f is the 0 vector, as usual. So this turns into, okay, so now we've got to compute the gradient here. The x derivative is 2x minus 1, 0, and then here I would get a 2 quantity x plus 2y minus 4, comma, that'd be the x derivative. The y derivative is going to be a 2y minus 2 plus 2 times the derivative of the inside in this case is going to be 2. So I'll pick up another factor of 2 to get a 4 out front. X plus 2y minus 4. And I want this to be the 0, 0 vector. So that's the gradient of this function. Yeah, I like some John Bellion songs. Yeah, John. Yeah, so this came from, I solved for z in the plane equation here. And this was the restriction that I want to impose, to only consider points on the plane. So then if I did this correctly, I plugged in this expression for z. Oh, okay. That was trippy. So I took z and I plugged it in here. And then that turns into that. That's where that came from. Nice. X term's going to be, it'll be 2x plus 2x, that's 4x. The y term is going to be 4y. And this is going to, what's the constant term? Minus 2 minus 8 is minus 10. That should be 0. And then similarly, the y derivative needs to be 0. So here, the x term is going to be 4x. Right, yeah. What is the y term going to be? It's going to be 2y plus 8y is 10y. And then negative 4 minus 16 is minus 20. Okay. There's our system of equations to solve. It's linear, so it shouldn't be any problem. Okay, so good question. Abhishek says, don't we need a domain? Yes. In this case, the domain is all x and y points. So it's definitely not a bounded domain. But the plane extends forever and ever and ever. So, yeah. And Jessica asks, will this give us the same point as method 1? Hopefully. Otherwise, something's fishy. So let's find out. The idea is that, yes, these are two different methods to get the same point. Okay, so that was a good question about the domain. I'll come back to that in a sec. So let's solve this system. If it were me, I would move the constants over and divide through by 2. This will turn into 2x plus 2y equals 5. And then 2x plus 5y equals 10. Oh, another music wildcard, Casey Musgraves. I love Casey Musgraves, yeah. Okay. So you're correct, Abhishek, that it's not a bounded domain, but it'll be fine in the end. Okay, so then what would I do? I would probably take this, subtract this. So take the second equation minus the first equation, and that would give me, the 2x's canceled out, I'll get 5y minus 2y is 3y equals 10 minus 5 is 5. So y is 5/3. And I think I've erased the point that we found in the first solution, but hopefully that's the same y value that we got. Oh, yeah, that's, so by that I meant take this equation minus this equation. That's how I think of it, but yeah. So I think that's the same y value. No. It happened again. Okay, my chat broke again. Hold on. Ooh. You guys are, yeah, I actually might do that if you don't mind. Okay. We're gonna rig up a solution here. I won't be able to chat with you. Oh, that's, yeah, if you don't mind.
Yeah, I zoomed it all in.
Okay, thanks. Okay, so my chat broke. Hi, it's Joe. I'm gonna be Janet in the chat. Yeah, we'll see next quarter if Zoom does this kind of stuff better, but even in office hours, like the past couple days, Zoom has been dying unexpectedly, and it'll like reappear, which is very silly. Okay. Thanks. We'll keep going. Oh yeah, we found the y value, so we should be able to find the x value, and then we'll be able to find the z value, and then hopefully that's the same point. So let me keep the z condition down here so I don't forget. So y is 5/3, so this tells me that, for example, 2x plus 2 times y is 10/3 is 5. Oh man, I don't want to, okay, you'll have to help me out. 5 minus 10/3 is 15 minus 10 over 3, which is 5/3. So x is probably 5/6. Hopefully that's what we got the first time. And then z is x, which is 5/6, plus 2 times y is 5/3, minus 1. And so this will be 5/6 plus 26 is 25/6, minus 1 is 19/6. And that checks out. So the point that we got doing this is 5/6, 5/3, 19/6. And that was the same point that we got with our first solution. Okay. Nice. We could just do this on Instagram Live next time. That'll be my plan. Okay, so there were two solutions, same problem, got the same point, different perspectives. To me, this is what's cool about 32A is that when you do multivariable calculus like this, you can take entirely different perspectives to get the same thing. My Instagram handle is just Joseph Breen, or Joseph J. Breen, maybe. Joseph J. Breen. Okay, moving on. You guys. Oh, I'm gonna get so many followers now. Yeah, I guess I do. I haven't posted in a while though, so don't get too excited. Maybe. I'm going to have a lot of people to follow back. Okay, I will after the review session. Maybe after the final's over, so there's no... Yeah. Let's do another limit. That was a lot. This one will be a little less crazy than the first limit that we did. Okay. This one will be a little different for a couple reasons. I think earlier, oh yeah, John. A little off topic. That was okay. Are you the one on the right or left? I'm neither of those people. Yeah. I think maybe Anna asked about, will we ever get a limit where we're not approaching the origin? That could happen. And here's an example. The other complication about this example is that it's going to be in 3 dimensions, which I don't think I've talked about with any of you guys yet. So here's what I want to do next. Same prompt as before, evaluate or show that this doesn't exist. The following limit. The limit as x, y, z approaches 0, 0, 0 of something. Let's do x minus 1, z minus 1. Over y minus 1 squared. Okay. For 3D, isn't it just parameterization? Or for more than 2 variables, does that matter? I don't know if I know what that question means. And Amans says 1. I don't know if I know what that... Oh, sorry. Yeah, that's what I screwed up. Thanks. 1, 1, 1. Good catch. I was on autopilot. Sorry about that. Okay, so the limit is as we approach 1, 1, 1, not the origin. If it was the origin, then yes, you could just plug it in. So I've done that with both limits now. Version 1, you can just plug in. Yeah, so the idea with any limit is like one way to attack it is to just pick parameterized approaches. We'll just have to be a little careful about how that works in 3 dimensions. Okay. Ideas? Well, try plugging it in now that I've fixed the problem again. Doesn't work, right? So Abhishek suggests moving along planes. Maybe. Okay, and then Anna suggests, what if we pick the approach where x equals y equals z? I like that. Let's try that. So suppose we approach via x equals y equals z. Now, the first question to ask is, are we allowed to do that? In this case, yes, because the point 1, 1, 1, it does satisfy these equations. So that's okay, that checks out. You could not do something like, you couldn't necessarily do something like z equals mx or y equals mx because those might not go through the point 1, 1, 1. So one thing to keep in mind is that because we're approaching some weird point, any kind of approach we pick has to actually contain this point. X, Y, Z, this one does because 1 equals 1 equals 1. So if I impose this restriction, what does the limit turn? This is going to the point 1, 1, 1 of this expression turns into x minus 1 times z is x, x minus 1, over x minus 1 squared. And that simplifies a lot. First of all, this thing, to send a point x, x, x to 1, 1, 1, it suffices to just send x to 1. So this turns into a 1 variable limit. And then this is x minus 1 squared over x minus 1 squared. That's 1. So by this approach, we get 1. Okay, so now what? So x equals y equals z is actually a line, not a plane. That's a line. Can you make a dummy variable t such that the limit as t approaches 1 is 1? Yeah, you could do it that way too. Yep. Now we've picked one approach and we got a limit of 1. That alone doesn't tell us anything, right? That just shows that along one method of approach, we get 1. So what next? Alonzo? Yeah, so I like that. So another simpler approach is like, what if we just pick, so in the chat, x equals 0 and y equals 0, that wouldn't work because that won't pass through the point 1, 1, 1. But if I impose the restriction, say x equals 1, yeah, and z equals 1, that would work. So the next approach, one thing that we could do is we could approach along the line defined by x equals 1 and z equals 1. And then I'll send z to 1. So if I impose this restriction, what happens? This limit is going to turn into, so I'm fixing x to be 1. I'm fixing, whoa, that was really big. I'm fixing x to be 1, I'm fixing y to be 1, and I'm letting z vary, and then I'm approaching the point 1, 1, 1. And then what does this turn into? It turns into 1 minus 1, 1 minus 1, over, oh, sorry, I said the wrong thing. I'm sorry. We're fixing x and z, and then we're letting y vary. I apologize. So when x and z are 1, I get 1 minus 1, 1 minus 1, and then in the denominator, I get y minus 1 squared. But then, this is just, first of all, this turns into the limit as y goes to 1. The numerator is 0. So this is just the limit of 0, which is 0. And that works because that shows by this approach we get 0. By this approach we get 1. 1 is not 0, so therefore the limit cannot exist. Alonso? Probably not. For something like this, you could probably restrict to just a plane. Like you could say, let me just restrict to the plane x equals 1. And then for any approach along that plane, it'll be 0. That's I would do this. Like I would pick a parameterized path. Like I would pick a single path, but it's probably okay to like pick a planar approach if you explain it well. Anyway, let me finish this off and then I'll look at the chat. Since 1 is not 0, the limit doesn't exist. Done. Cool. Okay. Can we not just put y equals 1? I would say that the domain of the function doesn't include y equals 1. So I don't think I would be allowed to approach like that. What if you set x and y to be 1? So same kind of issue. I don't think you couldn't, we're not allowed to set y to be 1 just because the domain of the original function kind of implicitly does not include the entire plane y equals 1. Jai?
If these were to not work, what would be like equivalence of like in two variables would be like x minus x squared?
Yeah, that's a good question. Like polar coordinates in 3 dimensions, sort of. It wouldn't be called polar coordinates anymore. You could do something called a cylindrical coordinate type thing, or you could do a spherical coordinate type thing, neither of which we've really talked about in this class. So probably I wouldn't worry so much about that. But there are analogs of polar coordinate transformations in 3 dimensions. Yeah. Okay. So then Abhishek asks, but we should be given the domain? Not necessarily. I think when you look at an expression like this, it's implicit that, like, you know, we can figure out what the domain is just based on the formula. Does proving that the limits don't exist, does this mean that the function isn't differentiable? It for sure means that at the point Well, yeah, yes. The function may not even be defined at the point that we're taking a limit of, but it definitely for sure implies that it's not differentiable. That'd be like, what's a dumb metaphor? No, never mind. I won't try to come up with a dumb metaphor. Okay, cool. Oh. Can I say that it isn't differentiable at 1, 1, 1, but differentiable at all other points? I guess so. I would say that the function's not even defined at 1, 1, 1. So the function's not even defined, so then it definitely doesn't make sense to talk about taking a derivative there. But on its domain, it would be differentiable. Yeah. Okay, cool. Yeah, so at all other points where y is not 1, it'll be differentiable. Let's see, what next? Let's let me do a quick problem, and then last night, I don't know if Audrey's watching, but she asked about doing a maximization problem on a disk domain. So I've got one of those planned too. Let me do a quick problem first, and then I'll do a global maximization problem. Okay, so next up is going to be excuse me. Here's the question. Is there a function f such that the gradient of f, and this is a 3-variable function, is yz plus 2x, comma, xz, comma, xy plus 2xz, question mark. That's next. A gummy break sounds good too, if I had any. We could take a water break. Collision versus, yeah, we can do that at some point. Oh, I guess I'm out of water. Nice. The world is truly ending. Yes.
The problem with that you did with the plane and the closest to it, like that function of xyz is the distance squared. Does it matter then, like, the point you found? Does it matter that the distance is squared?
Oh, okay. So that's a good question. Was about back in the problem that I did where I found the point closest to the plane. In the second solution, I did that by minimizing the distance squared function. And I didn't really have to worry about anything because I didn't actually care about the distance. Like a slightly different question would have been, find the distance between the point and the plane. In that case, I would care about the output of the thing that I was minimizing. Oh yeah, I'll rewrite this bigger on the board. Sorry about that in a sec. But because I was trying to find the point at which the minimum occurred, it didn't really matter what the function was doing. So like it didn't matter that it was the distance or the distance squared or something like that. I just cared about the point at which that occurred. And that is the same. I don't know if that answers the question. Okay. Okay, let me rewrite what I wrote. Sorry about that. So I want the gradient of f to be the vector yz plus 2x, xz, and then xy plus 2xz. And the question is there a function out there with this? Check the email really quick. Any ideas from real people or internet people? We could work it backwards. It's an idea. Okay, so a couple solutions for partial integration. You could think about it that way, or the other suggestion was Clairaut's theorem. And then Katie says specifically, what if we look at the xz and zx derivatives? That's probably what I would do. But you could also try to do partial integration here to just recover a potential function. And then probably what you'd find is that, well, I don't know what you'd find. Let me do Katie's idea, which is, I know what you'd find, but we don't know what we would find. This, if there were a function, this expression here would be the x derivative, and this expression would be the z derivative. So the suggestion is to take the z derivative here, the partial with respect to z of this thing, yz plus 2x. And if there were such a function, this would be f sub xz. Likewise, what if I took the x derivative here, d dx of xy plus 2xz is going to be y plus 2z. And if there were such a function, this would be f sub z x. And by Clairaut's theorem, we know that if there were a function, these would be the same. But they are not the same. So therefore, there is no function. Okay?
If they were to match, why don't you have to check why?
If they were to match, why don't we have to check why?
Why is that enough?
Because Clairaut's theorem says that all mixed partials are going to be the same in any order. So it's sufficient to exhibit one instance of failure. Think about that for a sec. Let me look at chat questions. So Aman's asking a similar question, is like, so do we also need to check fxy and fyx and like fyz and fzy? No. If you can just exhibit one instance of failure, Clairaut's theorem kicks in, because Clairaut's theorem says they all have to be the same. So if one of them isn't the same, then you're done. and that shows that there's no function. So let me write that up. So probably if it were me, I would say something like, by Clause's theorem, which I'm not going to try to spell, if there were a function f, then Clause's theorem says that f, for example, f sub xz and f sub zx are the same. But what did we just show here? Y is definitely not y plus 2z, so therefore there is no function. Done. That would be my solution, but you know, there could be okay, so a couple questions, both from Amans. So for instances of truth, so one thing you have to be careful about is that if the mixed, I don't know what's happening today. If all the mixed partials are the same, does that mean that there's a function? No. The only thing we can really do is show that there is no such function by exhibiting the failure of that phenomenon. But it is not the case that if all the mixed partials are the same, it's not necessarily true that there's a function. There's a potential function. That's actually really interesting, and it's very deep stuff. And I gave a challenge problem in section 1 week. Oh my God, what is my hair doing? So to show that a function exists, you either have to do this partial integration thing to just find it, or there's a lot of other fancy math out there that you learn in 32B or beyond that we don't really talk about in here, but it is a pretty deep question. So checking that the mixed partials are the same. Question, hand, no? Nice. Tricky stuff. See ya. Nice. So then the other question was, does the method of partial integration create a system of integrable derivatives? I don't know if I know what that means. Anyway. Moving on. How about that? Anyway, so this was similar to a problem that was on the homework from a couple weeks ago, but just with 3 variables instead of 2. But on the homework, there was a question exactly like, here's, you know, is there a function whose gradient is this? And I don't know how you guys did it, but I think the intended way was for you to check the mixed partials, show that they're not the same. Therefore, by Clause's theorem, no such function exists. Never mind. I'll talk about that some other time. Okay. Oh, yeah, see.
So if all the mixed partials were the same, would we just say it could be a function?
Then we just don't know. So if all the mixed partials were the same, could be, maybe not, hard to say. Yeah, exactly. It's very deep, actually. Okay, what was I gonna, oh yeah, I was gonna do a global extreme value problem. Okay. Super fun as always. Okay, so the prompt is, here's a function, as always. And what did I pick? xy times e to the negative x squared minus y squared. That's the function. I want to find the global extreme values on the closed unit disk. Find the global extrema on the closed unit disk. Okay. So last night we did an insane problem on a square that had a total of 10 points to check. I think this one will be better, but we'll see. Oh, and the difference is mostly in the domain, which is now a disk instead of something like a square. So the thing that we'll have to be a little more careful about is how we check the boundary. That'll be a little maybe different looking than how we checked the boundary last night. In any case, in these global extremization problems, your first step is always still to search for critical points on the interior of the domain, because those are candidates for global extreme values. So first step, as always, find critical points of F. How in the world do we do that? We take the gradient and find where that's 0. So first, what is the gradient of F? In this case, I might give myself some more room in case this is gross. And I'll get to sit down while I write it too. The gradient of F is going to be the vector. All right, so the x derivative here, we'll have to do the product rule. Take the derivative of xy first. I'll get y. Leave the other thing alone. Plus, I still didn't give myself enough room. That's okay. Plus, leave the xy thing alone and take the derivative of the other chunk, which by the chain rule is going to look like that. So that would be, I think, the x derivative. And then the y derivative will be very similar. By symmetry, it'll be, take the y derivative, you'll get, so comma, I'll continue down here awkwardly, x e to the negative x squared minus y squared plus xy e to the negative x squared minus y squared, and then this time times a negative 2y. So that's, sorry for looking ridiculous. First component of the vector, second component of the vector, those are the x and y derivatives. Okay. Then as usual, we've got a system of equations. I want both of these to be 0, and that's what we need to solve. So let me write that down. So our system of equations, also if I simplify this a little bit, on top here, both terms have a common factor of y e to the blah, 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 blah. So I can pull that out, 2x squared. That should be 0. And And then likewise down here, I set this thing equal to 0. Both terms have a common factor of x e to the blah, 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 blah. Leaving me with 1 minus 2y squared. That should be 0. That's our system of equations. My thought process here is I'll maybe pick this first equation and break this down into 2 cases. On the one hand, y could be 0. That would be one way to satisfy this equation. The only other way for this top equation to be 0 would be if this term is 0, just because the exponential part, we know that exponentials are never 0. Okay. Now, if y is 0, what does this equation tell me? This term here is 1. So I get x times this equals 0. That means that x also has to be 0. So I'll say that out loud, and if it's not clear, you can let me know. But if I assume that y equals 0, this equation tells me that x has to be 0. Then we have to consider this scenario. This tells me that x could be plus or minus 1 over the square root of 2. Oh, and then what? What does this equation tell me? If x is either the plus or minus square root of 2, this is non-zero. So then the only way for this equation to be 0 would be for this term to be 0. So this would imply that y would also have to be either the plus or minus 1 over square root of 2. Okay, so how many critical points do we get from this scenario? 4. All possible combinations, unfortunately. So I'll get 1 over root 2, 1 over root 2. I'll get negative 1 over root 2, 1 over root 2. I'll get 1 over root 2, negative 1 over root 2. And when they're both negative. Okay. So I guess we have 5 critical points so far. How's that? Okay. Why not include the zeros? I don't know if I understand the question. One thing to keep in mind is that these 2 scenarios are completely separate. They don't interact at all. One of those scenarios was when, don't we get a point like 1 over root 2, 0? The answer is no, precisely because these has to be 0. So there are no such points where these are mixed. Okay, so that's kind of annoying. We've got 5 critical points. Okay, so that's the question. This is actually a little interesting. Are those critical points that we care about? Yes. Why? Because they are in the domain. They are actually on the boundary of the domain. And that's okay. They are in the domain, so we do have to care about them. The question was, Oh, my question that I asked myself was, we found all these critical points. Are they in the domain? Because if they're not in the domain, then I can just ignore them. But each of these critical points does satisfy x squared plus y squared is less than or equal to 1. They in fact satisfy x squared plus y squared equals 1. So that means they're actually on the boundary of this region. Let me draw a picture. But that's okay. They are still in the region. So we do care about them. So where did I plug in the plus and minus 1 over? I didn't really plug them in anywhere. I considered the case where this was 0. That tells me that x has to be this. And then I used, well, I guess maybe if I plugged anything in, I plugged it in over here. Sorry about that. So I plug these into this equation, and I would have something non-zero times this. The only way for this to be 0 would be for this to be 0. And that's what I was going to do. That's the unit circle, sort of. And we found 5 critical points so far. 1 at the origin, and then these 4 points, which are like here, 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 and here. Okay. Now we have to check the boundary. So I want to keep this up. Whew. So next up is check the boundary. And the boundary in this case is a circle. So as always, there are multiple ways you can check the boundary in this case. Here's one method. You can parameterize the circle and plug that parameterization in to the function. Let me do that. So a parameterization for the boundary circle which is x squared plus y squared equals 1, is old news now. For example, we could do cosine t sine t. Here's a description of the boundary, but every time I describe a boundary curve, I have to give a parameter domain. So for example, here I could take t from 0 to 2 pi. So now I've described my boundary parametrically. What do I do with that? I erase some stuff first so that I can forget them when we need them. But I'll keep the picture up. What was I going to do? Oh yeah, so what do we do with this information? I plug this into the function I care about, and by doing that, I'm restricting the function to the boundary. So what I'll do is I'll consider f of x, I'm restricting to be cosine t, and y, I'm restricting to be sine of t. When I do this, I'll get cosine t sine t e to the negative x squared minus y squared. When x is cosine and y is sine, that's just going to be negative 1. So I get that. This is my boundary function. And that's what we'll have to maximize and minimize next. So let me call this g of t. And again, I care about this function on the domain 0 to 2 pi. Okay. So what do? We've got a one variable function. I need to find critical points and then check the endpoints. So I search for critical points of G. G prime of t is going to be, if I do the product rule here, I'll get a negative sine squared and then plus cosine squared all over E. And this quantity here will be 0 when, so this is 0 when the numerator is 0, which is to say sine squared of t is cosine squared of t. Okay. Now, like I said, this one's a little funny, but what am I saying? What's the solution or solutions of that equation? What t values solve that thing? Amans says cosine 2x equals 0. Yeah, you could think about it that way. You could use a trig identity idea. Yeah, so pi over 4 solves it, also 3 pi over 4, also 5 pi over 4, and also 7 pi over 4. So you could get that either by trig identity or by just thinking about when sine and cosine have the same absolute value. This tells me that t could be pi over 4, 3 pi over 4, 5 pi over 4, or 7 pi over 4. Now, what points do these correspond to? They correspond to these points that we actually already found. That won't necessarily happen. Like, it was kind of a coincidence that the critical points we found in the first step were already on the boundary, but it could happen. And it happened in this case. Now, the fact that these critical points were already on the boundary, did that mean we didn't have to check the boundary? No. You still have to check the boundary because there could be other points. There weren't in this case, but there could be other points. Finally, strictly speaking, the last thing we do have to check is points 0 to 2 pi. We sort of don't actually have to check them in this case, but don't worry about that. You should. So also check endpoints 0 and 2 pi. T equals 0 and 2 pi, which both correspond to the point 1, 0. And that would conclude the boundary analysis. And that would conclude all of the analysis. We've generated all possible candidates for global extreme values here. And it looks like we've got 6 points to check. And I might do what I did last night again and not plug them in. But what would you do? You would plug all of them in. No, let's do it. F of these two values is going to be 0. So let me call these names. A, B, C, D, E, F. I don't think this should be too bad. F of A and F of B, both of those have a y coordinate of 0. So f of those points will be 0. F of, let's see, C is going to be the same thing as f of E, which will be 1/2 times e to the negative 1. And then f of D will be the same as f of F, which will be negative 1/2 e to the negative 1. So, and then I'll look at chat questions. This is the largest value that we spit out. This is the smallest value that we spit out. So this is the global maximum value. The global maximum value occurs at the points C and E, and the minimum value occurs at the points D and F. And that would do it. That would be one way to do the analysis here. How would you check the boundary? Or, okay, a couple questions. How did you check that the endpoints were critical points? They weren't. Endpoints are endpoints. They're not necessarily critical points, but you always have to check endpoints. Oh, that's what Abhishek just said. Thanks. And then the other question was, how would you check the boundary if you hadn't parameterized the curve? The real answer is the only way to check the boundary is to parameterize the curve, but the other kind of thing you could do, which doesn't really feel like parameterization, is you could say, it's a little awkward in this case, but you could say like, oh, y is the plus or minus square root of 1 minus x squared. And then you could plug each of these in here to get a boundary function. That would break the boundary into two different parts, but you could do it that way. And yes, you have to check. And okay. Janet. Yep. Yeah, so the fact that the global max and min occurred at multiple points, that could happen. Cool. Okay. Done. All right, let's do another chain rule problem next. What did I pick? All right, so here's a function, as always. Let f of xy be xy plus e to the x plus y. Here's what I want to do. Let r and theta be polar coordinates, as usual. Compute the partial derivatives. Let's just do, I don't know, doesn't matter. Let's compute the partial derivative with respect to theta of f at the point when xy is 1, 1. That's a little weird sounding, but that's what we can do next. Feel. I gave us a function in terms of x and y, but I'm looking for a derivative with respect to theta. The idea is that if r and theta are regular old polar coordinates, what is the relationship between x, y, and r and theta? The polar coordinate equations that we know are x equals r cosine theta and y equals r sine theta. In other words, x and y both depend on r and theta. So here's the picture of the dependencies that we have. We've got f. F depends on x and y up there. But then x and y both depend on r and theta. And the thing that we're curious about in this problem is the change in f as theta changes. There are two ways by which that can happen. One like this, and then one like this. So the chain rule would say that we have to account for both of those. All right, so let me spit up what the chain rule says. So by the chain rule, the theta derivative of f, one way that we can get change is through this leg here. The chain rule would tell me take f sub x times x sub theta. I could write it like that. And then plus, I also have to account for this change. This would be f sub y times y sub theta. And that's what we have to compute. So let me compute this abstractly as a function first, and then we'll figure out what to do to evaluate at this specific point that I care about. So f sub x is this thing, or that's f. F sub x is going to be the x derivative of that, which is y plus e to the x plus y. That is this. Jeez. Something like that. And then what is x sub theta? The derivative of x with respect to theta is going to be negative r sine theta. Okay. And then I've got this stuff. So the y derivative is going to be similar. It'll be x plus e to the x plus y times, sorry, y with respect to theta is going to be r cosine theta. Okay. That's f sub theta as a weird function of 4 different variables. What I care about is the derivative at the point xy equals 1, 1. So I know that I'm going to plug in 1 and 1 for x and y. What do I plug in for r and theta here? That's what we'll have to figure out. So the next question is, what values of r and theta yield the point xy equals 1, 1? You can think about this algebraically with the equations, or you could think about it geometrically. the 0.11 is here. The angle is going to be pi over 4. And the radius would just be the distance to this point, which would be root 2. So it looks like r would be root 2, and theta would be pi over 4. So those are the values that I would plug in for r and theta here. And then for x and y, I would plug in 1 and 1. And that would do it. So let me finish that off. So f with respect to theta at the point x, y equals 1, 1 is 1 plus e squared times negative r is root 2. Sine of pi over 4 is root 2 over 2. And then plus 1 plus e squared times r is root 2. Cosine of pi over 4 is root 2 over 2. And that would do it. And actually, this simplifies a lot. I think this is 0. Nice. Does that make sense? I guess. Interesting. All right. So the theta derivative at this point is 0. Done. Another chain rule problem. Questions about that? Internet questions about that? Yeah, let me re-explain how I got r and theta. So the xy point that I care about is 1, 1. And let me redraw the picture bigger. Yeah, let me do that over here. So I'm told that I care about the derivative when x and y are 1 and 1. And I want to determine the relevant r and theta coordinates. What is r and what is theta? When we talk about polar coordinates, r is always the distance to the origin. Another way to think about this is that we know we have the equation x squared plus y squared equals r squared. So if x and y are both 1, this tells me that 1 squared plus 1 squared is r squared. Therefore, r squared is 2. Therefore, r is root 2. That's maybe a more methodical way to get this. And then theta is always this angle. And since this point lies along the line y equals x, the angle is going to be pi over 4. There are more methodical ways to find theta, but I wouldn't worry about it, to be honest. Couldn't I plug in r cosine theta and r sine of theta for y and x instead of Katie says yes, so I'll say yes too. And yeah, the more methodical way to get the angle for any xy point is to take the arctangent of y over x. But like I said, I wouldn't worry too much about that. I don't think it would come up. I think a geometric type argument is probably fine here. Cool. Yeah, so another way you could do this is you could just say, screw the chain rule. I'm just going to go back to my original function, plug in. So I have since erased what x and y are in terms of r and theta, but you could just plug that in here and here, and then I just have a regular old function in terms of r and theta, and I can just take the derivative, and I don't have to worry about dealing with the chain rule. That would definitely work. So yes, you could do that. What could happen is you could be given a problem where you are not allowed to do that. So you could have a problem which is designed to specifically test this chain rule stuff. So in this scenario, you could do that, and that's fine, but I would make sure, I would understand the chain rule, just because depending on the kind of information you're given, you might not have a choice, and you might have to do some chain rule stuff. But yes, you guys are correct. That would also work. Cool, cool, cool. I did that. Yeah, I am getting tired. I might not last too much longer, but we've covered between last night and tonight, we've covered a lot. Oh, let me do a, I know what I want to do. I want to find the equation of a plane. Nothing too crazy, but, and I did one last night. So let's do another. What did I cook up? What does it mean that the theta derivative is 0? Yeah, so what that means is, yeah, we could do a linearization problem too. Yep, see Shy. Good luck tomorrow. What was I saying? Oh yes, all that means is that if you're at a point here in the domain, if you change like this in an angular direction, I guess there's no change there. That's kind of what that means. Brain team, I like that. Oh yeah, tonight, I guess the test comes out in like 3 hours. Don't go to sleep though. Go to sleep, get a good night's sleep, wake up in the morning. That's what you should do. Don't pull an all-nighter starting this test. Okay, what do I want to do? Let 2x plus y plus z equals 1 be some plane, be a plane. And I'll also give us a line, and let r of t be 3t tt be a parameterization of a line L, and I'll call the plane P, containing the line which is perpendicular to P. Find the equation of the plane containing L perpendicular to P. Okay, that's what we'll do. So what's the deal? I could try to draw a picture, but I'll fail. So I'll do this with a piece of paper. Here's the plane. And I've got a line. And, you know, I don't know, it doesn't necessarily look like this or something. It might just be angled. So be like that. What we're trying to do is we're trying to find the equation of the plane containing this line and perpendicular to this plane. So that would look like this plane, if that makes any sense. That's what we're trying to find. Okay, so how do we do that? What I would think about is, okay, I know that I want my plane to be perpendicular to P. That means that my normal vector, exactly in the chat, my normal vector should be perpendicular to this normal vector. That's one thing I want. I also know that my plane should contain the line, which means my normal vector should be perpendicular to the direction vector of this line. So to summarize that, I want my normal vector to be perpendicular to both the normal vector here and the direction vector here, which means I can get that kind of a normal vector by taking the cross product of the normal vector and the direction vector. That's correct. So let me write that down. A normal vector for our plane is going to be, I'll take the normal vector for P, which is 2, 1, 1, and I'll cross that with the direction vector for the line, which I can get by picking off the coefficients of T, so this would be 3, 1, 1. And then we have a cross product to compute, and that'll be the normal vector. Yep, you got it. And then we can get a point using the line, and we will be good to go. All right, so let me attempt to compute this cross product. 2, 1, 1 cross 3, 1, 1 is going to be 1 minus 1 is 0. 3 minus 2 is 1, and then 2 minus 3 is negative 1. And this will be the normal vector for the plane that we want. Now, to get the equation of a plane, I need a normal vector, but I also need a point. So how do I find a point? Well, one of the things that we're told is that the plane should contain the entire line L. So to get a point, I can just pick my favorite point on the line and use that. So a point on L, or a point on the plane, is, for example, R of, I don't know, 0. That's the point 0, 0, 0. That's got to be on the plane. So therefore, the equation of the plane is 0 times x minus 0 plus 1 times y minus 0 plus 1, plus negative 1 times z minus 0 equals 0. And it looks like this simplifies to y minus z equals 0. That would do it. Yep. We did it. Found a plane. Questions about that? Let's see. All right. Watch the feed from yesterday. So a couple questions. Did you have a question, John?
Can you visualize the beginning of this problem?
Yeah, I can try. So the question was, can I redo the visualization that I did? Let's do this. I want to do it for the camera also. Here's the plane. I was going to do something ridiculous. Okay. Let me do this, actually. Instead of using a piece of paper. Whoops. For the moment, this will be a better way to visualize this. Picture the whiteboard as being P. So here's P. And then I've got a line. And again, who knows what it looks like? Maybe it looks like that. What are we trying to find? We're trying to find a plane which contains this line, but is also in the line and be perpendicular to the whiteboard. It would have to be the plane that is coming like directly right at you. So then the question is, I want a normal vector for that thing. How could I get that? Well, I could take the normal vector out for this plane, cross the direction vector for that line. That would give me a vector pointing just like this, and that would be the normal vector for that plane that we want. That's the visualization. Okay, some other chat questions. One of them is, how do you know when to set the plane equal to something like blah, blah, blah equals D versus equals 0? It's the same, and to me, it's up to personal preference. So the idea there is that you can describe a plane either by saying AX plus BY plus CZ equals D for some number D, or completely equivalently, you could say A times X minus X naught plus B times Y minus Y naught plus C times Z minus Z naught equals D, equals 0, sorry, for some point X naught, Y naught, Z naught on the plane. I probably, if you go back through your notes the entire quarter, have never used this. To me, this just comes from this. And here I don't have to think about what D is going to be because I just plug in these points. But they're equivalent because if you just distributed this and moved everything over to one side, you would get blah, blah, blah equals D. So it's kind of up to you. It's personal preference as to which one you use. That was one question. Another question is, could I go over the two methods for finding tangent planes? So one thing I'll say, I might punt on that. I did make a YouTube video exactly about this, and I can't remember what I titled it, but I think it's like called Computing a Tangent Plane in Two Different Ways or something like that. So I'll suggest to watch that video. Probably anything I could say right now, I'll just say more poorly than I say in that video. But the rough idea is that if you have a surface, it's the graph of a function, Or you can realize the surface as a level surface for a 3-variable function. In that case, you can get a normal vector by looking at the gradient of the 3-variable function. But like I said, if any of you guys are more curious about that, I'll punt to my YouTube video from a couple days ago. How do I do the questions where I have a vector and I need to split it up into 2 vectors, one perpendicular and one parallel to another vector? So I've got a vector. Here's the vector I want one component to be parallel to. So the first thing I would do is I would take that vector and project it. And that will give you the parallel component. And then you take this vector minus this vector to get the perpendicular component. That was a verbal answer. I can write that down too, or draw a picture if you want. Nice. I was going to say, what else do I have prepared? I have an arc length problem, but like I said, I did an arc length problem last night, so maybe I'll say you can, I think it was the first thing I did last night, so you can rewatch that if you want arc length. Oh, what else? I guess I have another limit that we could do. How about this? Usually I can go a little longer, but I'm really tired. And we've covered pretty much everything. So let's do this. I'll do one more limit, and then I'll hang around to chat for a few minutes. More Q&A, or we can just chat. And then we can say goodbye on the internet for now, and then call it a night. Sound good? The last question. All right, one more limit. It'll be quick, I think. We'll see. But before people start jumping ship on the stream, I said this last night, but just so all of you guys know, it won't be that juicy. I used most of the juicy. Yeah, this one won't be super. It'll be a little juicy. But just so everyone watching knows, I will be a 32 BTA next quarter. And one possibly good thing about all this online stuff is that even if you're not in my section, or even if you're not in my lecture, everything I have to say about 32B is going to be filmed and streamed and put on the internet. So keep an eye on this channel. Keep an eye on my website, because I'll post Zoom links to like office hours and discussion sections. I'll probably make videos and put them on YouTube. So anyway, you can, I'm TAing for Noah White. But again, even if you don't have him, you can seek me out. Okay. Happy to offer any kind of wisdom I have to give. One more. Evaluate or show that doesn't exist the following limit. Let's do the limit as xy approaches 0, 0, as usual, of what? X cubed y. Whoa. Okay. Yeah, I'm starting to lose it now. X cubed y over 2x to the 6th plus y squared. Does it exist? Etc. So what's the deal? Same flow chart as always. First thing I think about is, can I plug it in? Nope. I get an indeterminate form, 0 over 0. Okay, so the next thing I'm bouncing around in my head is, does approaching along the axes tell me anything? For example, if I fix x to be 0, the whole thing is 0, so I get 0 that way. Yeah, so, yeah, and Aryan's got the good suggestion, which is we should approach along the axes. We'll get 0, and then pick an approach like y equals x cubed. Unfortunately, an approach, we could also think about y equals x, but I don't think that will get us anywhere. You can try, though. I think y equals x cubed is the way to go in these problems. Anyway, upstairs a little bit earlier was a question about, so like next quarter, even if you're not in my discussion section, can you tune in on Zoom? Yeah, I think so. I'm going to plan on posting Zoom links on my website, so it'll be public information. So you can watch, I guess anyone in the world with a Zoom account can watch. So, yeah. So you could try linear approaches, but I think what you'll find here is that all lines also approach 0, in which case this wouldn't tell you anything. But first I would say approach along the x-axis, say. That, then I'm fixing y to be 0. The function I get here is x cubed times 0 over 2x to the 6th plus y plus 0 squared. Well, this whole thing is 0, so this is just the limit as x goes to 0 of 0, which is 0. That was one approach. Now we need to find another approach which gives us something different, and there were some other suggestions, and like I said, I don't think y equals x works, but let's try. So what if I try y equals x? And I'll just do this in my head. This will turn into x to the 4th over 2x to the 6th plus x squared, which divide the top and bottom by x squared. You get this. And this goes to 0. And any line is going to work the same way. So linear approaches will always give you 0 here. So unfortunately, that won't work. Yeah, I wouldn't even use L'Hopital's rule. I would just divide through by x squared, and then it's clear. So we need to find another approach, and Aryan had the good idea, which is, what if we pick y to be x cubed? So approach along y equals x cubed, then something magical happens. What does this turn into? The limit as x comma x cubed is y approaches 0, 0 of x cubed y is x cubed over 2x to the 6th plus x cubed squared. What happens here? This turns into the limit as x goes to 0. On top, this is x to the 6th. And on the bottom, this is 2x to the 6th plus x to the 6th, which is 3x to the 6th. X to the 6th cancel out. This is just 1/3. And 1/3 is not 0, so therefore the limit doesn't exist. So since 1/3 is not 0, the limit doesn't exist. Okay. Nice. Oh. Yeah, so up here, this one term here kind of saves the day, and that means we don't go to infinity or anything like that. Okay, I'm gonna officially call it there. Like I said, I'll hang around to chat for a few minutes, but otherwise, good luck tomorrow. Don't stay up and wait for the test. Just go to bed, get a good night's sleep. Don't worry about it too much also. It's been a crazy week. I think when we're grading and when Jeff is determining final grades, we'll take that into account. So try not to worry about that kind of stuff. Just do your best. Things will be okay. Question? Let's see. Yesterday I did I did a linearization problem. That would be good to do. So if you want, all the examples I did last night are hyperlinked in the descriptions on the videos. So if you want to check out the linearization problem I did, you could do that. Otherwise, it was similar. Like I guess I classified some critical points last night with the second derivative test. I didn't do that tonight. I computed curvature. You should know how to do that too. There were a couple other random things, but that was the gist. See, John, good luck tomorrow. You are all welcome. Oh, nice. Thanks, Mia. I will wear the crown with pride. A little bit, yeah. But it's not the end. You can see me next quarter. You can come say hi next year, hopefully when we're all back here in person. My favorite Ariana Grande song is, it might be Bad Decisions is up there. Better Off is up there. Yeah, it's very unrelated or underrated. We have to use this solution template for our answers. I think, to be honest, I don't really know. I ignored all the logistical information about the exam because I don't have to deal with it, so I'm not sure. No. I have a really bad memory, actually, I think. Yeah. God is a Woman is up there also. It's a great one. I did, yeah. What does right side up mean? What's my workout playlist? I actually don't listen to music when I run or work out, believe it or not. Maybe I might be. I don't know. It's kind of soothing to just be in silence and get in the zone.
Would you just listen to the gym music then?
Well, at K-Rec, they don't play music at all.
Really?
Yeah. So it's just it's just the sound of people grunting and
Is it a deal breaker
see you guys.
if you found a gym that played music?
Nah, I'd be okay with it. Like the gym in my hometown just plays the same 3 songs over and over again. It's like Back in Black, Crazy Train, and I don't know, some other random rock song. And it's a little annoying. But do I have a math playlist? No. My favorite Disney movie is Tangled. Tangled is actually one of my favorite movies ever. And I think it's one of the more underrated princess movies. Not that I watched that many of them, but favorite math YouTube channel is definitely 3 Blue, 1 Brown. Yeah, if you guys haven't watched any 3 Blue, 1 Brown videos, you're in for a treat. Favorite movie, Tangled is up there. What else is up there? Oh, what's it called? Number File's pretty good. Here's the right-hand rule. I don't know if that's what you're asking about. Favorite, I also like the Coen brothers a lot. Let's see, Star Wars fan? Not really, to be honest. When I was a kid, we had the shitty Star Wars with Jar Jar Binks and Anakin as a kid where they do pod racing. I don't know which episode that one is, but it's the one that no one likes. Yeah, I like Fargo, but my favorite Coen Brothers movie is probably my brain is literally dying. What's the one in sepia film with George Clooney? George Clooney's in all of them, but they're back in the like 30s. Oh, Brother, Where Art Thou? That's probably my favorite. Anyway, yeah, so we had episode 1 on VHS, and so I watched that over and over and over as a kid. So purely for nostalgia's sake, that's my favorite Star Wars movie. That's my terrible, controversial Star Wars take. I have seen Good Will Hunting, but it's been a long, long time. I remember liking it. It's due for a rewatch now that I'm into math. Hail Caesar. I don't know if is that a Coen Brothers movie? I don't know if I know that one. Also, to be honest, in terms of movies, I really like horror movies. Like The Descent is one of my favorite movies. I like a lot of shitty horror movies. Favorite math movie? I don't know. I don't know if I have a favorite math movie. The Descent is great. I have not seen Children of the Corn. I wasn't huge on A Quiet Place. I liked Get Out a lot. I have not seen Us, though. Stand and Deliver, I don't know if I've heard of that one. I really like The Blair Witch Project. That's one of my favorites. Annabelle, I don't think I've seen. I've seen The Conjuring. And Annabelle's like one of the spin-off type things, right? Nice. I'll have to watch Hail Caesar. All right. See you, Abhishek. I have seen Hereditary. Stand and Deliver is a calculus movie. Okay, not a horror movie. I liked Hereditary. I don't know if I loved it. I love The Shining. That was one of the first horror movies I saw as a kid, and it really scared me. So to me, it's to this day one of the scarier movies that I've seen. But yeah, I love The Shining. I was a big Stephen King fan in high school as well, so I've read most of his books. Except I have not read Dr. Sleep or seen the movie. So I actually don't know about it right now, which is The Stand, which is about a plague that sweeps the earth and kills off like 99% of the population. That's probably my favorite Stephen King book. What other movies do I like? Honestly, so The Stand is insanely long. It's like 1,000 pages long. And the end kind of gets weird. But the first third of the book, like the first 300 pages, is just Stephen King describing the destruction of this plague and describing everyone dying. And it's like the most amazing thing in the world. So you could read the first like 300 pages of The Stand and then stop. Favorite book genre? Yeah, I like horror books. Like I said, I went through a big Stephen King phase. I guess if I had to pick a genre, that would be it. I have not read World War Z. No. I can't believe 26 people are still watching this right now. Yeah, I guess so. Oh, Jessica asked a long time ago if I like country music. Yeah, I like some country music. Yeah, like if you count Casey Musgraves, I mean, that's pretty much pop music, but there's some other country music like the Turnpike Troubadours and stuff like that. No, just go to bed. Don't wait for the exam. You have plenty of time tomorrow. Just get a good night's sleep. Wake up. Exam is only 10 questions, in case you didn't know. So it's not like 15 or anything crazy like that. No, I won't tell you the problems on the test. Also, it's don't worry about it. It'll be fine. There's a couple tricky problems. I will go missing on the internet starting at midnight, and unfortunately, you won't be able to contact me. So you might get a follow on Instagram from me at some point, but that'll be the extent.
I'll just show up.
Oh, well, I mean, if you have questions about like if you have questions about the logistics of submitting something like that, or if you have an issue, like you can obviously email Jeff. Like if you email us saying, help, how do you do question 2, then that's probably not good. But if you have logistical questions or something, I do have the same initials as Jar Jar Binks. Nice. Oh, I've never noticed that. My middle name is John. Joseph. I don't know why it keeps doing that. Oh, I've just realized that I'm still using your computer. Damn it. Sorry about that. No, I feel really bad now. All right. I'm gonna sign off. I'm tired. I'll go to bed. Goodbye, good night, and good luck tomorrow. And I will see you guys around next quarter. Cool. Sorry about that.
Yeah, I wanted to stay for the Q&A. That's cute.
Thanks for